Hello everyone, my name is Zizheng. I come from Shanghai Jiao University EPCC Lab. Today I will give a talk to introduce RunD, a lightweight secure container runtime for high-density deployment in a high-concurrency startup in serverless computing. In the first section, I will briefly introduce what serverless and fast are, and what challenges we may meet for multi-tenants in serverless computing. First, what is serverless? According to Berkeley's view, serverless equals fast plus BAS. Developers upload their codes as functions to the fast system. User triggers a function through events, like HTTP requests. The fast system allocates computing resources and interacts with the backend services to execute functions. When hosting function invocations, traditional containers only provide process-level allocation, as they are implemented based on namespace and cgroups, and sharing host kernels across different instances. To this end, secure containers that achieve the same allocation with the traditional virtual machines are often preferred. Secure containers often create a normal container within the lightweight microVM. MicroVM is for allocation, and the container is for abstraction. In such a way, users can build serverless services based on existing container infrastructure and ecosystem. However, each microVM needs to load a guest kernel, so it cannot provide low overhead when allocating functions. Before investigating challenges that using secure containers may introduce, we first need to realize what makes serverless special. First, the small container specification in a serverless computing brings the requirement to deploy containers densely on a node. For instance, 47% of Lambda functions run with a minimized memory specification in AWS. Second, the actual memory usage of a container may also be smaller than its specifications. As Eryu reports, about 90% of the applications never consume more than 400 MB of memory. Third, in serverless platforms, each function invocation is short, and a large number of function invocations may arrive in a short time. For example, more than 200 container launch requests arrive within 1 second on a node. Finally, it is a common phenomenon that thousands of containers may collocate on a node. A node can host 2048 containers if there is no other overhead. Considering these characteristics in serverless, we can know that when using secure containers to handle invocations, there is a basic guarantee of low response latency and two requirements of high concurrency startup and high density deployment. So, does the current secure containers like Kata can meet our requirements? We make an experiment using Kata containers. When starting 100 or more Kata containers concurrently, there is a distinct performance degradation. It may take more than 10 seconds to create a sandbox. The CPU usage and overhead are also significant in a host. When deploying more than 1,000 Kata containers, the microVM's memory footprint already occupies most of the memory space. If we start a new container now, it will take 1.5 times as long to create. The above observations indicate that current secure containers have a concurrency and density bottlenecks in serverless computing. In the next section, we will analyze the bottlenecks of secure containers and where do these bottlenecks come from. For the guest rootfs, It can be exposed to the container runtimes in the microVMs through two interfaces to construct the image layers. File system sharing, like virtualfs, and a block device like virtualblock. Both of them have advantages and limitations. For example, block devices have good read and write performance. However, time-consuming of preparing large volumes in high concurrency. It does not support the page cache sharing between the host and guest operating systems. When virtualblock backend reads rootfs files into the host page cache, the mapped can turn reproduce the same page cache in the guest. This issue of duplicated page cache brings a high memory footprint overhead. File system sharing like virtualfs resolves the problems of duplicating page cache. However, it loses the good write performance. In addition, each container has to employ a client daemon to support virtualfs I/O operations, leading to heavy CPU usage when many containers collocate. So our first insight is that the current secure container fails to discriminate between serverless platforms and traditional IaaS environments. In the microVM of a secure container, the guest operating system, the struct page for memory management, and other components like BaseOS, ShimV2 agent consume additional memory space. The memory overheads of a 128 MB container, 94 MB and 168 MB with kata firecracker and katakumi respectively. The overhead increases with the memory specification of the container. The average memory footprint of a single microVM can be reduced by sharing the text read-only segment among multiple microVMs. Mainstream microVMs achieve it by mapping the kernel files to the guest memory directly. The per microVM memory overhead of katakumi and kata firecracker reduces. However, the overhead is still too large for a serverless container with only 128 MB memory specification. Our second insight is that the current microVM introduces heavy memory footprint in serverless computing, where small memory specification containers dominate. For the host cgroups, it is designed for resource control and abstraction of processes. In serverless computing, the frequency of function invocations shows high variation. In this case, the secure containers are frequently created and recycled. For example, 100 clients commit cgroup operations. 1,000 cgroup operations are performed per second, and 10,000 cgroups are maintained in the host. However, the Linux kernel introduced several global locks, like mutex locks, to serialize cgroup operations. When spinner cgroups experience the optimistic spinning if they fail to acquire the lock, it will lead to heavy CPU consumption and a belated exiting of the critical section. So our third insight is that the host side overhead of cgroups prohibits the high-density deployment and high-concurrency startups in serverless computing. Simplifying the cgroup design and reducing the critical section introduced by the mutex locks are fundamental solutions. So how does RunD resolve these challenges? We have three main optimization points: read-write splitting rootfs, condensed kernel and pre-patched image, and lightweight cgroups with cgroup pool. When designing RunD, we have a key implication for serverless runtime. The negligible host-side overhead in a traditional VM can cause amplification effects in serverless with high density and high concurrency, and any trivial optimization can bring significant benefits. To this end, RunD shows various advantages in serverless computing. So how does RunD work? Step 1. The container D forwards an invocation to RunD. Step 2. RunD prepares RunC container rootfs for VMM. The rootfs is split into read-only and read-write layers. Step 3. Hypervisor uses microVM template to create sandbox and mount rootfs. Step 4. A lightweight cgroup is renamed and attached from the cgroup pool. RunD make guest-to-host optimizations in these steps, and we will detailedly introduce them. For read-write splitting rootfs, we leverage the feature that user-provided code data is read-only for the operating system. Meanwhile, the data in the local memory or storage generated in a sandbox will not be used by subsequent function invocations due to the stateless feature of serverless computing. The temporary and intermediate data generated during the function execution is not required to be persisted, so RunD handles them in different ways. The sandboxes can share the read-only layer on the same node, and the writable layer has to be prepared separately for each sandbox. When creating a bilateral block device for a new sandbox, a built-in storage image is created and linked to the storage image template using reflink. Reflink enables storage image template to share data with built-in storage image in a copy on write fashion, so it ensures that user functions can perform writing as usual without persisting data on the local disk. To reduce the memory footprint, our key goals are condensing the guest kernel and improving the shareable part of the VM. Especially, self-modifying code of kernel text segments only occurs at the startup phase, after which the kernel code area becomes read-only after initialization. In this case, sandboxes experience the same initialization phase and generate predictable self-modifying code segments. So RunD generates a pre-patched guest kernel image file that already patched with self-modified code segments. Serialized cgroups operations in the host become one of the bottlenecks of secure containers with high concurrency startup and high density deployment. RunD proposes lightweight cgroup with cgroup pool to resolve these challenges. The lightweight cgroup decreases the total number of cgroups and the system costs. Rather than creating the cgroup for each subsystem, we aggregate necessary cgroup subsystems into one dedicated lightweight cgroup. The implementation of the joint cgroup controller helps RunD reduce the redundant cgroup operations when the container is started, significantly decreasing the total number of cgroups and the system costs. The cgroup rename, as a special case, is a lightweight operation without acquiring any global lock. Cgroup pool with renaming eliminates the time-consuming cgroup creation and initialization. For each created container, RunD simply allocates an idle cgroup, update the state to busy, perform the cgroup rename operation, and then attaches the container to this renamed cgroup when the container is started. With above designs, RunD can make serverless runtime more lightweight. In this section, we will introduce our evaluation process. We compare RunD with the state-of-the-art secure containers, kata containers. Specifically, we use three popular configurations of kata containers: kata QMU, kata template, and kata FC. Kata QMU uses QMU as a microVM hypervisor. Kata template uses QMU while integrating container templates. Kata FC uses lightweight Firecracker as a microVM hypervisor. In other tests, we only create pod sandboxes without other containers inside through the CI/CTL command. The actual memory usage of a container is collected using the SM command. The results show that RunD is able to start a single sandbox in 88 milliseconds and launch 200 sandboxes within 1 second, with minor latency fluctuation and CPU overhead. As observed, RunD has the least memory overhead among 4 runtimes, and does not increase with the memory specification. The memory overhead is less than 20 MB per sandbox with RunD. It supports to deploy over 2,500 sandboxes on the node. We also deploy RunD as Alibaba serverless runtime and verified in production. It indeed guarantees the low response latency and meets the high concurrency startup and high density deployment requirements. Finally, we give our conclusions on RunD. RunD proposes guest-to-host solutions to secure containers for high density and high concurrency targets in serverless. The practice including a better container rootfs implementation based on read-write splitting for serverless. The method to condense the guest kernel and improve kernel sharing by a pre-patched kernel image. The host-side lightweight cgroup design and the rename-based cgroup pool management. Our next track presentation help rather than recycle, elevating code startup in serverless computing through inter-function container sharing, also focus on basic guaranteeing of low response latency when code startup occurs. It proposes to accelerate time-consuming container specialization if it needs code startups. You can also contact us by email with any questions. Thanks for listening.